now we move on to part 2 of the question. So show that if the straight line ax plus bx equals to 1, where ab is not 0, is a normal to the curve ax minus, a over x minus b over y equals to 1, then a squared minus b squared equals 1/2. Okay, so this is part 2 of a question. So it's always wise to think about, what method you used in part 1 and try to replicate it. All right, so most step questions require you to use the information from previous parts cleverly. Okay, so part 1 was in last video, so the same method applies here. So firstly, we established the gradients of the two curves. So I have ax, so let me write down the two lines first. So I have that. All right, so the gradient of that we established in part 1 would be minus a over b, and the gradient of this one we also established in part 1 actually, but the plus becomes a minus. Okay, so it's up here but without the minus. Okay, so that's ay squared on bx squared. Okay, I hope the implicit differentiation is okay. So this time is a normal. Okay, in part 1 it was a tangent. Well, it has the same gradient, I guess, but this time is normal. Okay, so we have to use the properties of gradients of normals. Okay, so these two would multiply to give -1. Right, that's the gradients of normals. Okay, so the negatives go away. So I could write this as a squared y squared equals to b squared x squared. Okay, so a squared y squared equals to b squared x squared. So essentially that means that ay equals to plus or minus bx. Okay, similar argument in part 1 here. Okay, so if ay equals to plus or minus bx, then we could use this in our equations. So our equations were ax plus by equals 1 and a over x minus b over y equals to 1 as well. Okay, so I have ay equals to bx, or ay equals to minus bx. Okay, so I have these two cases here, and actually one of them does not make any sense. All right, let's see if we could spot which one it is. Okay, so if we use the second formula, so if we said we had a over x minus b over y equals to 1, right? So let's say our y was equal to bx over a. Okay, y was bx over a, then that would be saying that a over x minus a over x would equal to 1. Okay, that looks very suspicious, right? Because that makes no sense. Okay, so that proves that ay could not equal to positive bx. Okay, it just gives us a contradiction here. Okay, so ay equals minus bx instead, and we have to do the same thing with our equations. Okay, so let's sub into the first equation. So we want a squared minus b squared, right? That means we don't want x's and y's. Okay, we don't want them. So we would want a, so the x would be minus a y on b, yeah, and plus by, well, actually let's keep the ax for later, you'll see why. Okay, and so let us keep the ax here, ax plus b. Okay, so y is minus bx on a. Fine. Okay, so y kept to x is because we could see from the second equation, we know that a over x plus a over x equals to 1. This time it's a plus, so it makes much more sense, and we could easily see that 2a equals to x. Okay, so that information from the second equation gives us a very useful information. Okay, so we could get rid of the x and we sub in for the a's, then we could leave a's and b's themselves. Okay, so we do what I just said. So plus b times minus b 2a. So that equals to, what does that equal to? That equals to 1, doesn't it? Okay, so that's 2a squared plus the a cancels out, so it's minus 2b squared, isn't it? Equals to 1, which yields the result a squared minus b squared equals to half, which is what we want. All right, so that's all of question 1.